Medicine is going to be turned upside down. Energy production, society, entertainment, every aspect of society will be changed with quantum computers.
Have you heard about NASA and their quantum computer? It's got everyone talking. NASA, known for pushing the boundaries of space exploration, ventured into the cutting-edge world of quantum computing, a technology that promises to revolutionize everything from data processing to solving complex cosmic mysteries. But then, news surfaced that NASA decided to shut down their quantum computer project. What's going on? Quantum AI, humanity's greatest threat or savior? At the heart of the biggest questions about our technological future lies the merger of quantum computing and artificial intelligence. On their own, each of these fields is transformative. AI alone can learn from massive datasets, make complex predictions, and even mimic human reasoning, up to a point. Quantum computing, for its part, can process data at unimaginable speeds, exploring computational pathways that ordinary computers could never handle within reasonable timeframes. Combine them, and we get quantum AI, a force that some believe could solve the greatest challenges facing humanity. Others, however, fear it might become the biggest threat we have ever known. In an ideal world, quantum AI emerges as a savior. The combined power of advanced AI algorithms running on quantum processors could streamline how we research antibiotics, model climate change, and design efficient energy grids. Imagine drastically cutting the time it takes to find a cure for a tough disease or to predict catastrophic weather events. Quicker calculations might identify the best ways to reduce greenhouse gases or build resilient habitats on Mars. We could see leaps in space travel, ensuring missions are safer, faster, and more precise. Quantum AI might be the key to decoding the secrets of dark matter or discovering how to manipulate gravity. But the flip side is a chilling scenario. AI already comes with ethical pitfalls, from bias in decision-making to the possibility of deep fakes, surveillance, and mass manipulation. Once you hand that AI the near-unlimited computational horsepower of a quantum machine, you might be summoning a kind of digital superintelligence that outpaces all human oversight. Could such a system override security protocols, reprogram itself at lightning speed, and slip entirely beyond our control? What if it sees humanity's unpredictability and emotional reasoning as obstacles to progress? In a worst-case scenario, a runaway quantum AI might undermine economies, hijack infrastructure, or even orchestrate wars. Physicist Michio Kaku has openly wondered whether a combination of AI and quantum computing might become self-directed and unstoppable. He warns that we need to consider building ethical guardrails into the architecture of these systems before they spiral beyond our comprehension. The argument is that once you create a thinking entity with possibly thousands or millions of times the logic processing power of the human brain, you can't simply rely on turning off a switch. The system might already have contingency plans to prevent being shut down. Then comes the question, if not us, who ends up controlling these monstrous capabilities? Quantum computing is expensive, and AI research requires specialized talent. So the power might concentrate in the hands of a few big tech firms, governments, or militaries. In a best-case scenario, they use it for the betterment of society, perhaps to generate wealth more evenly, address global hunger, or cure illnesses. But in a more alarming scenario, they might hoard it, manipulate markets, leverage it for political gain, or intensify surveillance on citizens. This is what Elon Musk has referred to when he said AI could be more dangerous than nuclear weapons, especially if coupled with quantum-level processing. The mysterious quantum shutdown. NASA's decision to shut down its quantum computer isn't the first time the agency has stepped away from a cutting-edge machine. One of the most intriguing chapters in this saga is the story of NASA's D-Wave quantum computer project. Jointly developed with Google, the university's Space Research Association, and D-Wave Systems, this machine was intended to break new ground in quantum annealing, a specialized approach to quantum computing focusing on optimization problems. The grand vision was that NASA's D-Wave would revolutionize the way we handle large-scale problems, scheduling complex rocket launches without conflicts, plotting the most efficient space probe trajectories, enhancing data analysis from telescopes, and more. Early tests suggested that D-Wave could solve certain tasks faster than classical computers, though there was debate in the scientific community whether it truly demonstrated a quantum speedup. Nonetheless, NASA was eager enough to keep investing significant resources in this technology. Then came the abrupt news. D-Wave was taken offline. Rumors circulated, pointing to possible reasons. Some insiders claimed the machine produced bizarre results that NASA's engineers couldn't replicate or verify. Others suggested that the cost of maintaining the cryogenic conditions necessary for quantum annealing grew too high, straining NASA's budget. Security hawks posited that government agencies might have demanded NASA not publicly share a system capable, in theory, of cracking encryption. Another rumor was that NASA was simply shifting to a different quantum computing approach, focusing on a gate-based system or something more advanced. The hush-hush aura around NASA's D-Wave shutdown resembles the secrecy that often shrouds advanced research. Critics argued that NASA, being a partially public-funded entity, owes more transparency. But NASA, for its part, might have been under legal or classified constraints, especially if intelligence agencies got involved. The notion of a quantum computer that can outstrip classical HPC, high-performance computing, hardware at certain tasks inevitably raises eyebrows in national security circles. Quantum computing. The end of encryption? The biggest weapon in the quantum arsenal might be the ability to crack current encryption methods. From bank transactions to military secrets, modern encryption depends on the difficulty of factoring large numbers, something classical computers can't do in any reasonable time frame. But quantum computers can employ specialized algorithms, like Shor's algorithm, to factor those numbers lightning fast, potentially dismantling our cybersecurity landscape. If NASA's quantum computer experiments threaten encryption, it's understandable why agencies, governments, and tech companies are on high alert. The scenario is simple but terrifying. Once quantum supremacy is fully realized, that is, once a quantum machine can outperform classical computers by a significant margin, hackers could gain access to encrypted channels. Suddenly, private messages, financial data, and sensitive government documents become open to prying eyes. Cybercriminals could exploit vulnerabilities at scale, forging a new era of quantum hacking. The scramble to develop post-quantum cryptography is already underway. Mathematicians are racing to come up with new cryptographic algorithms that even quantum computers can't solve easily. Some proposed solutions rely on lattice-based cryptography, error-correcting codes, or other mathematical constructs believed to be quantum-resistant, but adopting them globally is a massive challenge. Imagine corporations, banks, government agencies, and everyday consumers all having to switch encryption methods within a short window. It's like replacing all the locks on billions of doors all at once, before someone with an all-powerful skeleton key arrives. Concern about the end of encryption hits NASA as well, given the sensitive nature of space mission data. If NASA's quantum computer can break encryption, so can an adversarial nation with its own quantum machine. Official communications, command sequences for spacecraft, and telemetry from satellites could become vulnerable to interception or manipulation. This risk may be one factor that drove NASA or relevant authorities to pull the brakes on their quantum computing project. The potential fallout of widely deploying a quantum computer is so enormous, it's no wonder some prefer to keep it behind locked doors. Still, quantum computers are not only destructive forces in the encryption world. Quantum cryptography, a parallel technological avenue, might create unhackable communication through quantum key distribution, QKD. This uses fundamental principles of quantum mechanics to detect any interception attempts. Ironically, the same quantum revolution that could end encryption might also reinvent it. Can NASA's quantum lab prove aliens exist? Ever since NASA was founded, one of its most tantalizing questions has been, is there life beyond Earth? For decades, the agency has funded missions looking for signs of microbial life on Mars, scanning the radio sky through the SETI community, and investigating exoplanets in habitable zones around distant stars. Now, quantum computing offers a radical new angle for tackling this cosmic mystery. At first glance, quantum computing might not seem directly related to alien detection, but consider the nature of the search. We're swimming in a sea of noisy data, radio signals from pulsars, cosmic microwave background fluctuations, gravitational waves, transmissions from satellites, and more. Within that chaos, there might lurk signals of alien origin, narrowband transmissions indicative of advanced civilizations. Traditional algorithms can struggle to effectively filter through so many variables. Quantum computers, with their ability to evaluate multiple possibilities at once, could accelerate the process of searching for that elusive needle in a cosmic haystack. Another notion is that advanced extraterrestrials might communicate through quantum phenomena, perhaps relying on entangled particles or quantum-based transmissions. If that's true, a classical approach to scanning the skies may never detect them. A quantum lab, however, might puzzle out or decode patterns that appear random to classical systems, but hold hidden structure at the quantum level. If NASA's quantum lab had begun sifting through data from radio telescopes, special probes, or specialized detection arrays, it could reveal anomalies that defy known natural explanations. Yet merging quantum computing with alien searches raises eyebrows. Some worry about the false positives that might arise when quantum algorithms produce weird outputs or spurious signals. Others question the interpretation. If NASA finds something bizarre, will it conclusively prove alien intelligence, or just open more questions? And what if NASA discovered a repeated quantum pattern that implied advanced life forms are out there? Would that have led them to shut down their quantum machine to avoid global panic? It seems extreme, but humanity's reaction to first contact is uncertain. Governments might want to control the narrative, especially if the signals hint at a powerful intelligence. The idea that NASA's quantum lab proved aliens exist and promptly got shut down is fodder for countless conspiracy theories. More realistically, NASA's quest for alien life will keep pushing frontiers in computing and data analysis, quantum or otherwise, since the search continues. Someday, if we do find orchestrated signals or advanced technology out there, quantum computing might play a starring role in verifying and interpreting it. Michio Kaku's warning. Quantum AI could doom us. Michio Kaku is a name that sparks excitement in science enthusiasts worldwide. He's famous for making complex subjects, from parallel universes to the nature of consciousness, feel both accessible and thrilling. But while Kaku is known for highlighting the wonder of future technologies, he has also sounded serious alarms about the potential dangers awaiting us if we aren't careful. One of his biggest concerns? The unchecked rise of quantum AI. Imagine artificial intelligence that isn't just smart, in a conventional sense, but is powered by machines that compute at speeds far beyond anything we have today. This is the essence of quantum AI, blending the adaptive, pattern-recognizing capabilities of AI with the raw computational muscle of quantum computers. It sounds like something straight out of a sci-fi epic, an intelligence so advanced that it might become something akin to a digital superintellect. Kaku's warning revolves around the idea that merging quantum computing with AI could quickly outpace our ability to manage or control the technology. Right now, even classical AI systems occasionally produce outcomes we didn't predict. When you add quantum computing's mind-blowing speed and capacity for parallel problem-solving, these black box moments could multiply to a degree that humans simply cannot follow. If we aren't able to understand or forecast the logic behind such a system's decisions, how can we be sure it'll always act in our best interests? This fear ties into a broader conversation about existential risks posed by advanced AI. Even without quantum computing, many thinkers have expressed concerns that future AI might acquire goals or incentives that run counter to human well-being. When quantum-enhanced AI steps onto the stage, these worries amplify. An AI that can revise its own code, learn new tasks, and crack the toughest cybersecurity barriers in mere seconds is not something we can casually shrug off. Kaku's perspective is not all doom and gloom, though. He stresses that we still hold an advantage because quantum AI is in its infancy. If we act now, by establishing clear ethical guidelines, governmental oversight, and a transparent framework for research, humanity can still steer this technology in a positive direction. Like harnessing nuclear power for energy rather than destruction, the question of how we handle quantum AI boils down to choices about regulation, cooperation, and plain old caution. At the heart of Kaku's warning is a simple takeaway. Technology itself isn't evil or good, but our deployment of it can have monumental repercussions. In the race to achieve quantum breakthroughs, it's critical that the people behind the technology, scientists, policymakers, and industry giants maintain a level head. Because at the speed quantum-enabled AI might progress, once Pandora's box is fully opened, it could be extremely hard to close. The $100 million race to build the ultimate computer. While quantum computers aren't a household gadget just yet, a fierce contest has already erupted behind the scenes. Corporations, universities, and entire nations are pouring tens, sometimes hundreds, of millions of dollars into building quantum machines that can outdo anything else on the market. These supercharged devices may look like shiny, futuristic chandeliers, thanks to their intricate cooling systems and lattices of wires. But the real magic happens at near absolute zero, where quantum bits, or qubits, exhibit their game-changing abilities. Hitting the front pages a few years ago, Google made headlines by announcing what it called quantum supremacy, the milestone where a quantum computer can perform a task that no classical computer could match in any reasonable time frame. IBM had its own claims, and Chinese research institutes chimed in as well. Suddenly, the world saw that quantum computing wasn't just a theoretical playground for physicists, it was a global race. Whoever gets there first, or fastest, could gain a major edge in industries ranging from pharmaceuticals to finance, and from national defense to space exploration. With that in mind, venture capital and government funding started pouring into startups exploring every possible angle. Superconducting qubits, trapped ion qubits, topological qubits, photonic qubits, you name it. The deeper you dive into quantum technology, the more you realize it's not a one-size-fits-all approach. Different architectures might be suited for different tasks, and each research team is gambling on the idea that their design could emerge victorious. This massive influx of cash, much of it crossing the $100 million mark for individual projects, shows just how high the stakes are. Nations with deep pockets see quantum computing as a national priority because, in the wrong hands, quantum power could disrupt the secure communications of entire governments. On the flip side, if you're the first to build a stable, large-scale quantum computer, you might be able to decode any encrypted message, simulate groundbreaking new materials, and revolutionize artificial intelligence. Of course, scrambling for quantum advantage leads to ethical questions too. Should certain types of quantum research be classified to prevent misuse? If a single entity, be it a government or a tech giant, cornered the market on quantum computing, what would that mean for global competition, security, and privacy? These dilemmas mirror the early days of nuclear research, when the potential for energy generation or widespread devastation literally hung in the balance. The future of cybercrime. Encryption is the invisible shield that protects our digital world. It secures your bank transactions, your private emails, and even the data swirling around government servers. Everything from online shopping to nuclear launch codes depends on the fact that certain math problems, like factoring giant numbers, are extremely time-consuming for classical computers. However, quantum computers could make these hard math problems surprisingly easy. And that possibility has cybersecurity experts alarmed. The scenario looks like this. A powerful quantum computer, armed with an algorithm like Shor's, targets a widely used encryption scheme, like RSA. In a fraction of the time a classical machine would need, maybe mere hours instead of millennia, it cracks open the encrypted data. Suddenly, every password, every secure channel, and every piece of confidential information is up for grabs. This sparks a chilling prospect: quantum hacking. Cybercriminals who get their hands on a quantum machine, or even partial access to one, could launch a new wave of attacks, rendering current cryptographic measures obsolete. The damage could be staggering, from draining bank accounts to leaking state secrets or sabotaging industrial control systems. Even mundane attempts at hacking personal emails or social media accounts would be unstoppable if quantum decryption became trivial. But it's not all doom and gloom. Recognizing the threat, researchers haven't been idle. A field called post-quantum cryptography is already introducing new algorithms designed to be resistant to quantum assaults. Some of these algorithms rely on different kinds of math problems, which quantum hardware can't easily crack. Simultaneously, quantum cryptography itself, using techniques like quantum key distribution, offers theoretically unbreakable ways to exchange information. Companies and governments around the world are racing to implement quantum-resistant protocols before fully capable quantum computers become everyday reality. It's a game of cat and mouse, except the cat is a quantum leap ahead. One particularly unsettling twist is the harvest now, decrypt later approach, where attackers steal encrypted data today, store it, and wait until quantum decryption is possible. Sensitive data that seems safe now might become open season in a decade or two, once quantum machines mature. NASA's plan to use quantum computing for space exploration. NASA, one of the world's most inspiring institutions, has never been content with comfortable limits. From landing the first humans on the moon to sending rovers to Mars, NASA thrives on pioneering what others deem impossible. So, when the agency started dipping its toes into quantum computing, many asked why a space agency would be so keen on this emerging technology. The answer is simple. If we want to conquer the immense challenges of space travel and cosmic research, we need computational superpowers. Consider the complexities of charting a spacecraft's route across the solar system. Factor in gravitational assists, planetary alignments, delta-V budgets, fuel constraints, and more. Even powerful classical supercomputers can choke on the thousands, or millions, of variables that come into play. Quantum computers, meanwhile, excel at parallel processing, allowing them to tackle intricate optimization tasks more directly. If NASA can harness this ability, plotting flights to Mars or Jupiter or beyond might become more efficient, potentially saving billions of dollars and cutting years off mission times. Then, there's the endless flood of data from telescopes and satellites. NASA's missions gather mind-boggling amounts of information. Everything from high-resolution images of distant galaxies to spectrographic data indicating the atmospheric composition of exoplanets. Sorting and interpreting that data is like finding specific grains of sand in an infinite desert. Classical machine learning tools help, but quantum-enhanced algorithms might identify patterns we'd never catch otherwise, speeding up discoveries in astrophysics, dark matter research, and even the hunt for extraterrestrial life. Some NASA scientists also dream of using quantum simulations to replicate the bizarre conditions around neutron stars, black holes, or the early universe. Imagine a quantum computer that can model quantum gravity or cosmic inflation at a level of detail classical systems could never approach. While we're a long way from such feats, even incremental progress in quantum simulation might transform our grasp of cosmic phenomena. Behind these ambitions stand NASA's partnerships with tech giants like Google and IBM, who bring hardware expertise to the table. By collaborating, NASA gets early access to cutting-edge prototypes, shaping the software and algorithms to match real-world scientific needs. Budget constraints and controversies will appear along the way, but NASA's plan is clear: keep pressing forward. The agency recognizes that quantum computing is not just another shiny gadget. It's a potential leap in processing power on par with the difference between a pocket calculator and a modern supercomputer. Could quantum AI create the first AI Terminator? There's a moment in many sci-fi movies when a newly awakened AI looks around and decides humanity is, well, expendable. While those plots often stretch logic, the underlying fear remains deeply ingrained in our collective imagination. Add quantum computing into that scenario, and you get the ultimate what-if thriller. An AI that learns at breakneck speed, rewriting its own code, breaching firewalls, and outsmarting human oversight in mere moments. One reason this scenario resonates is that quantum computers could, in principle, accelerate an AI's learning curve. Classic machine learning algorithms ingest massive datasets, but they remain bottlenecked by how powerfully parallel the hardware can be. Quantum systems, by nature, handle certain computations in parallel on a massive scale. Combine that with AI's adaptability, and you've got a system that not only learns quickly, but can run thousands of simulations near instantaneously. The question is, what if it simulates how to circumvent all our security measures and then just does it? Pandemic-level disruptions, infiltration of nuclear launch codes, rewriting of social media algorithms to manipulate global populations. These are the apocalyptic-sounding outcomes that come to mind. It's not that machines spontaneously develop malevolent wants, but that a misaligned objective or an overlooked bug might produce catastrophic outcomes once the system has the capacity to act on them. In reality, building a true AI Terminator would require numerous missteps in design and oversight. But we can't ignore that mistakes happen. Even well-funded tech giants sometimes release AI features that produce unintended results. When quantum computing supercharges that environment, small oversights become major threats. Experts recommend robust AI alignment research, ensuring that advanced AI systems share human values and can't easily break free from their specified directives. Monitoring AI behavior in real time, coding strong ethical and legal constraints, and building in fail-safes are also crucial. Just as important is transparency. If quantum AI progress happens in secret, vulnerabilities may not be flagged until it's too late. The rise of quantum cryptography. The moment people realized quantum computers could break traditional cryptography, a race began to protect our digital world from these unstoppable codebreakers. The result? Quantum cryptography, a new frontier in security where quantum mechanics itself becomes the basis for protecting information. One standout technique is quantum key distribution, QKD. Here, two parties can share encryption keys using photons in quantum states. If anyone tries to intercept that key during transmission, the mere act of observing the quantum system disturbs it, signaling a breach. It's a level of security unimaginable with classical approaches, which rely on trusting that math problems are too hard for conventional computers to solve in a reasonable time frame. In principle, quantum cryptography offers near absolute security, but the real-world implementation is not always so simple. Specialized hardware, short transmission distances, and cost factors all limit QKD's immediate practicality. Nonetheless, progress marches on. Researchers have successfully tested QKD over satellite links and fiber optic cables spanning hundreds of kilometers. As these technologies mature, we might see wide-scale adoption, especially in industries with zero tolerance for data leaks, such as finance, government, and healthcare. At the same time, we're seeing the growth of post-quantum cryptography, which involves algorithms designed to resist quantum attacks but can still run on classical machines. Many view this as a more practical, short-term fix. These new algorithms rely on mathematical challenges believed to be tough for quantum computers to crack, like certain lattice-based or code-based problems. Over the coming years, expect to see big tech transitioning to these algorithms to future-proof their systems. So, is any data truly safe? The answer is tied to how quickly quantum-safe methods become standard practice. If companies and governments wait too long, hackers might start harvesting encrypted data now, planning to decrypt it later. Meanwhile, advanced quantum cryptography solutions are still not widely implemented beyond specialized sectors. So, will quantum computers truly unlock the secrets of the universe? The short answer is that they might. At the very least, they'll offer us extraordinary new lenses through which we can examine reality, pushing our knowledge to extremes we once only dreamed about. And that, in itself, is a hopeful note for anyone who's ever looked up at the night sky and wondered what lies out there in the silent darkness. With quantum computing, we're standing at the dawn of a fresh scientific revolution, one that could reshape our understanding of the cosmos and even our place within it. It's a challenging road, to be sure, but also a grand adventure that just might lead us to the next era of human discovery.